Okay, so you can vary the width and length. So maybe we want a 5 by 5 sheet. So how close I can get here. So that's something would be something like a 5 by 5 sheet. Or so let's just do a standard sheet of paper. So a standard sheet is 8.5 width by 11 length. It's as close as I can. Okay, that's the best I can do for. So this is we're mimicking now an 8.5 by 11, but you can change that anywhere you want. And so then again, you can, just like ours, the value n, he's got it as a slider called cut, and so you can cut out squares. So maybe we cut squares of 2.5 inches about. Something like that. Okay, he's got another view here. So the second view is then removing the squares altogether. Okay, so you could have the squares there or not. What's that? At 0, it's just showing the paper. The view is 0 view is just showing the original paper. Okay, the 1 view shows the highlighted cuts, and the 2 view shows no, the cut's gone. The square cut's gone. So did someone say that's awesome? Just wait. Okay, so watch this. Now what's n for? What's n for? So now do you understand what the open top box problem is about? Does that help? You probably already had an image of it, but
if we can do that instead of the 2D one,
yes.
Will that count?
Yes, that will count.
Will you give us like extra credit?
Much extra credit. Okay. So now if you want, you can also show the squares as you're folding up. You can leave the squares there, and they just stay on the ground. Yeah, you know. So you know what these boxes are for? You know what these boxes are for? They're for holding the squares that you cut out. Sorry. Okay. All right. So you can, and then. All right, and then so even midway, you can change things on the fly. So even if you started to fold, up, and you can still change the cut size. You can even still change the width. So midstream. That's impressive. And there's nothing, again, so he's built this in the XYZ coordinate system, okay? And everything about this is just mathematics. It's not, as you're learning, it's not command lines that telegraphing calculator to, okay, make the side fold up, you see? It's mathematical. So by changing the value of n, it's a mathematical function that takes that value of n and gives that plane the right angle for whatever n it is. Okay, so what do you observe here about n is when we're folded up is 1.57. What's that about? So what?
Pi over 2.
What's that?
Yeah, pi over 2.
Pi over 2, and why does that make sense?
Use rotating each side by pi over 2.
Right. So n equals 0. So what does n stand? So what quantity does n stand for?
Theta.
Yeah, it's this angle of rotation. So when you reach pi over 2 is when you've flipped it up 90 degree, upright 90 degrees from the original. Okay, what do you think? So basically, this is a great thing about graphing calculator. It's as powerful as you know mathematics for. If you can imagine something, and you can produce the mathematics for it, graphing calculator can show it. That's what's so great about this. I mean, yeah. So that, like I've said in a previous class, the more I teach year after year, I have ideas of what I want to show. It's just a matter of can can I get the math together and represent it mathematically so that graph calculator will show it. So maybe, I don't know, maybe extra credit, or maybe what we'll have is I will actually show you this and have you explain what's going on.
Kind of long.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. After the 4 sliders, it's like 13 or 14 command lines. So that's not exceptionally long. So is this someone who knows what they're doing? Yeah. Yeah, so this is all about transformations.
Oh, so you can use if conditionals.
Yeah, we'll be doing that. We'll be doing that. Okay, any questions on that? Okay. So let's go back to this. Now actually, this is what you're responsible for in your Wednesday project, but actually my version of this has more to it. So I'm going to turn the axes on. Okay, and this is what I use to teach about rate of change in my pre-calculus course. Can you see it? So again, what I showed you before and what I showed you in the video, that's what you're responsible for, okay? But in my file, it's just a piece. It's just a part of this other kind of graphing animation. Okay, so let's go back to this and let's talk about we're looking at the quantities of length of the square cut out and resulting length of the box. Length of the square cut out and resulting length of the box. Okay, so when I increase the length of the square cutout, what happens to the length of the resulting box? Bennett.
The length of the resulting box shortens.
What's that?
So the length decreases.
Okay, so as you increase the cutout length, he's saying the length of the resulting box gets shorter. Would you agree with that? That's a fair statement. Can we be more specific? Say more about that. Yeah, Danielle.
It gets shorter by, like if x is the length of the square,
Okay.
then the length of the box is going to be like 11 minus 2x.
So, okay, so as I increase the length of the square, so that's what that will be. But as I increase the length of the square, what will happen to the length of the resulting box? Is what I'm asking. So he said it will get shorter. So can you be more specific about how it will get shorter? Kyle. That's Kyle. In the black shirt.
I'm sorry, I missed the question.
Okay, so as I increase the length of the square cutout, what will happen to the resulting length of the box? Can you be specific about it?
It'll take the original length of the box, and then it'll get reduced by twice as much as the length of the cutout.
Okay, so you're kind of saying the same thing as Danielle. I'm not asking about the final quantity length. I'm asking what happens to the length as we increase this length of the square cutout. Is that a handout?
Well, I was saying something about the base of the larger box would be a lot smaller.
Be a lot smaller. Okay. Yeah. So the base gets smaller as we increase the, and so the length gets smaller, and that's what Ben said. Be more specific. How does the length change as the cutout length changes?
The length of the base is getting, so like as the cutouts get larger, the length of the base is getting twice as small. So like for every change, it has twice the change negatively its length.
Okay.
I kind of word that weird.
Steven, did you hear what Richard said?
Kind of.
Did you understand what he said? Could you explain it? Raymond, did you hear what Richard said?
Kind of. But what I'm thinking is as the length of the square increases, the length of the rectangle of the paper decreases by twice the length of the square.
Okay, so he said as the length of the square increases, the length of the resulting box decreases twice as much as, is that what you said? Something like that. Twice as much as the square increased. Jackie, what do you think? Did you hear what Raymond said? Did you understand what Raymond said?
Well, I feel like all of them are saying similar things, but decreasing by 2 times
Okay, decreasing by what's decreasing by 2 times the what?
the original length of the box is decreasing by 2 times the length of the cutout.
Okay. Okay, so is that the same as saying that the length of the cutout will be 11 minus 2x? Man.
Because that's focusing on the change.
Okay.
By just saying 2x, you have a fixed x value. But
Okay.
we're focusing on the change of x as
Okay.
it's increasing,
Okay.
which is a different type of value.
Okay. So, yeah, Carter.
As the length of the cut decreases
Decreases, okay.
or increases.
Increases, okay.
As the length of the cut increases at a certain rate, the length of the new rectangle or the box decreases at twice that rate.
Okay. Yeah, Danielle.
Just to word that a little differently.
Yeah, sure.
The length of the box will change at a rate of -2 times the change of the square, the length of the square.
Okay. Daniel, do you understand what Danielle said?
I was trying to comprehend what Matt and Jackie and Danielle said.
Okay. Oh, sorry, I meant to turn the light off. But the screen down's good too. All right. Okay, so let's go back to. So these are lots of good ideas. Let's go back to this view with the graph. I think I need to make it one more smaller. Okay. So here I'm showing that when the cutout side length is 0, what's the length of the resulting box? Not much of a box, but it's at least the bottom of it, right? Okay, so now I'm going to increase the cutout length by, I don't know, how about 0.5? I'm going to increase the cutout length by 0.5. Tell me what's going to happen to the length of the resulting box. Julia.
So we increase the cutout length by 0.5. You're decreasing the length of the box by 1 inch.
And can you explain why?
Because you have half an inch on one side
Okay.
that you're taking out,
Okay.
half an inch on the other side that you're taking out. And those added up equal 1 inch.
Okay. Okay, so how can I show that change from that point? How can I show that change in the cutout length? How can I display on the graph a change of the cutout length of 0.5 inches? Jessica. So here I am at 0 cutout length and 11 inches. How can I display on the graph that I'm gonna increase the size of the cutout length by 0.5 inches?
I guess you would move that arrow to, wait, that's cut out by like inches, right? So I'm just looking that arrow to 0.5.
Okay, yep, so I'm gonna move that to 0.5, and then how can I, then once I move it there, then it'll just be the new point that I get. I wanna show that change. How can I show that change?
Would you have to do it in relation with the length? Or no? You don't have to do
Okay, I just want to show a change of 0.5.
Oh,
Michelle,
would you have
one more try.
the point at 0 and the point at 5? That way you can have a difference of the change or the 2 points.
Okay, yep, so you could show both points at once. That would be one way to do it. Or I could.
I was thinking of like a horizontal line.
Yeah.
0 to 0.5.
Let's see if I can do this here. So if I could do a horizontal line right there, would that would show a delta x change of 0.5. And then you're telling me that if I do that, what will happen? If I actually now invoke that change, Stephen, what will the result be?
The length of the box would decrease by 1 inch.
Okay, so let's see if I can do this a little bit better here. Does that work? Yeah, that works. Okay, so I'm going to do that. Okay, and did it go down? If it went down 1, what should be the new length of the box? So the delta y was? 1. Was it 1? What's that?
-1.
Steven says -1. Is it 1 or -1? Negative. Okay, what if I do the same thing again? Richard? Now from there, I'm going to increase the cutout side length 0.5 again.
So the length of the base is going to decrease by 1, or so -1.
You think another -1?
Yeah, if you're going from 0.5 to 1,
Okay.
it's going to be twice as much, so that's -1.
Okay, so why is it guaranteed that every time I increase the side length by a half, the resulting length of the box goes down by 1? Does that happen every single time? Why? Why is that guaranteed? Anyone explain why is that guaranteed here? Every time I increase the side length by 1, you're telling me, or a half, sorry, you're telling me for every increase of the side length by a half, the resulting box will decrease by 1. Is it true? Always? Grant, why?
We have a constant rate of change between the resulting length of the box and the cutout. So each time you cut out a consecutive piece, it's going to take twice that much off of the previous box.
Okay, so he's saying that no matter how you increase the side cutout length, will always decrease that length by twice as much. Victoria, you agree?
Yeah, I was going to say that's a constant.
Yeah, that's the rate of change. Okay. All right, what if I increase the cutout length by 1.5? Janae, what will happen to the side length of the resulting box if I increase the cutout length by 1.5?
Will be -2.
-2. What do you think? Let's see. Kathy, you agree with that? -2? -3. So is it -2 or -3, Janae?
Yeah, -3.
-3. Okay, and then 1, -2. All right, so what relationship can we write then for changes in y to changes in x? Daniel?
Delta y divided by delta x equals
Were you thinking something else, Carter?
I was going to say delta y equals negative 2 delta x. Close to the same thing.
Okay. Is the length of the cutout proportional to the length of the resulting box? Is the length of the cutout proportional to the length of the resulting box? No.
No, it's not.
Why not?
Because there's no constant rate of change between those two. It's the change that's proportional, not the length.
Okay. Okay. Richard, what do you think?
I'm kind of thinking what Matt said.
Can you say more? Can you explain?
So,
Is the length of the resulting box proportional to the cutout side length?
I don't think so.
Don't think so.
No.
Carter.
Let's test it. We have
Yeah.
the points.
Yeah, we would have to
Do we do X
test
and
several.
L or Y?
Sorry, yeah, X and L. That's great. All right, so yes, that's a mathematician right there. Let's analyze the numbers. Let's do it. So what do we know? So we started out at X equals 0. L was?
11.
We increased it by a half, so we got to a cutout length of a half. And what was the length of the 10? And then we did it again, same thing. We increased by a half and we got to 1. And what's it now? 9.
Okay.
So Richard, explain.
So in order for the lengths to be proportional, is you'd have to have the constant proportion between the y and the x values at every point.
Okay.
I mean, a good way to tell if a relationship isn't proportional is to look at the very first value. So when x is 0, L is 11. Well, the ratio would be 11 to 0, which it's undefined. And then we go from 10 to 0.5. Well, now the relationship is a 20 to 1 ratio.
Right.
Then we go a 9 to 1 ratio.
Right. So clearly you don't have a constant ratio of your two quantities. Okay. But we do have a constant ratio of changes, right? So you see here, as the cutout length, what you said, as the cutout length increases, the length decreases twice as fast. Okay, so we can show that. If we want to show every point, how would we show every point? Okay, then we run out of room for our cutout at what? 4.25, so we can't go any further than that. Okay, so questions on that discussion? So that's just, that's very similar to what I did with my pre-calc students about two or 3 weeks ago, was I took them through. And then the next thing I did, I have a similar, I'll open it up here. I have a similar one for the volume, and we talk about the same things. As you increase the cutout length by a certain amount, what happens to the volume? And so what I'm showing here now, so we analyze the same thing. We take some changes in X and find the corresponding changes in volume now. And we analyze, and what is our conclusion when we analyze changes in cutout length and changes in volume?
Conclusion based on what?
So in the last time we concluded that we have constant rate of change, that the length is changing by -2 of whatever the cutout length changes.
That means at some point, some length of the cut, we're going to have a peak maximum volume for the box.
What about how these two are changing together?
Oh, quadratic.
It's actually cubic, but it's, so the idea is not constant rate of change. We can't write, so we come to the conclusion we cannot write, sorry, delta V. So it's like, what's the value of K for this relationship between volume and side length? That's supposed to be red, by the way. Doesn't exist, right? That doesn't exist. Okay, so just to review, I want to review the how we built up the equation of a line. So suppose that, I'm just going to make up some numbers here. Suppose we have a piece of paper and we've cut out side lengths of, let's say it's a really large piece of paper. So 20.6 centimeters is our cutout length. And the resulting length is, I don't know, 113.7 centimeters. So we got like a really big piece of cardboard sheet. And all we know is that we've cut out side lengths of 20.6 and the resulting length of the box is 113.7. So can we write the length of the resulting box in terms of, or as a function of, x, the cutout side length? All right, so I want to just walk through this the same way. Does anyone remember what was our process to build up this linear function? Where did we start with? Remember?
Finding delta x.
Delta x. So basically, we're going to pick some other x value, some other point that we know, or that we don't know, but that's going to represent every point on the line. So we have a point xy, represents any other point that we want on the line, or every point on the line. And so what would delta x be, Daniel?
Which ones are starting in?
So we're starting there, and we'll end at x.
X minus 20.6.
So that's the change in x from our given point to any point on the line. Okay? And then, how can we get delta y? Using constant rate of change. So using constant rate of change. So I want to do this a little bit differently than last time. But so we've got a totally different size of sheet. What is the constant rate? Now, I'm still cutting out squares out of the corners, but my sheet is some kind of a different big size, unknown, in the centimeters now. What's the constant rate of change? Rochelle?
It's still going to be -2.
Why?
Because no matter how big your paper is, you're still cutting out equal size squares from each side
Okay.
at the exact same moment.
Right, okay. So, yeah. All right. So how can we use that fact, and we have delta x, what is delta y equal to? -2. Okay, and so this is a little bit different than what we did last Wednesday. So this, writing the equation of the line means finding that value right there. So it's like, what is that? And so what we can do is we can call that the new y. And we have everything we need now to get the new y. Where does the new y come from? Starting at the old y. And how would we get from the old y to the new y? Add or change in y, right? So if you have a starting value of y, if you add the change, you get the new value. Yeah, Jackie.
Which points are like with what on your picture? Like what is that representing?
That's that one. And that's that one. So that was misleading. So what I was doing by that was by saying the focus here is writing the equation of the line means identifying what that value of y is. If we go to x, then what's the corresponding y? So the new y equals the old y plus the change in y. Okay, so that's how we can write the equation of the line. This y right here equals, what's this? 113.7 plus -2 times. Jessica, ask me. Or go ahead.
Okay. So I was looking at the change in x, and I'm assuming we change x by a length of 1, whatever.
No, this point can be any point on the line. See, x, y can be any point that you want on the line.
So if I want,
So if you want to change from 20.6 to x, well, how much change will you have in x?
so if I change from 20.6 to 19.6, you mean?
No, it's x, y representing every point on the line. Every point on the line, x, y.
I think we're just getting stuck with like the fact that our depiction is saying that x is larger than the old x. So what happens when x is smaller than the?
Is that what you're saying? So what if x is down up here? So what would the change be from 20.6 to x? If you took x minus 20.6, what kind of value would you get? You know, if x is back here.
Oh, it was smaller.
So you're going to take x, you're still going to take x minus 20.6. You're going to get a negative, right? But what about the change? Isn't that a negative change? It's a negative change, so it works out. Whether x is greater or less than 20.6. Does that help?
Oh yeah, but with the y, could be positive.
You do get it? Yeah. So, right, so if this is a positive change, meaning x is greater than, then the change in y will be negative. You see? And if x goes back, and delta x is negative, then our change in y will be positive. It'll increase that length. It'll be negative 2 times a negative. Does that make sense? Okay, so this is what we call, if we didn't last time, point slope form. It's very convenient. It's a lot. It's a lot more convenient than just always. If you always focus on y equals mx plus b, there's a lot of disadvantages to that. This always works, or it always is convenient, I should say. Whereas y equals mx plus b isn't always convenient. And sometimes the value of b doesn't really have meaning in the situation. Okay, you have to come up with some kind of virtual situation that is similar but isn't really real to make sense of what b would be. Okay, but this will always work when you have constant rate of change. Okay. Any questions? So this would be our L as a function of x. For that particular, whatever sheet of paper resulted in this particular point, that will give you the length of the resulting box given any cutout length x. All right, and we know what everything means, right? Change in x, change in y, starting value of y. Anybody have a question? Okay, so it leads us to our next little project. Can I erase this? So I think if I were to change this, I would make this bigger relative to what's going on here. Got a little too small compared to this. But actually what I used half the screen, so I had it like, I had both the volume and the length on the screen at the same time. So I had that for over here for this length function, and then I had the volume one over here. So I was showing them both simultaneously. But it might be more helpful to make that animation as you're changing these, make that animation a little larger. So comments or questions about this? Not only the point slope form and linear stuff, but just as a visual, as a discussion, as something to build a discussion around. Any comments?
Matt and I are kind of curious as to how you got the arrows. Was that more of like an image thing, like you did with the
It is. It's an image thing. So it's if you go to, so you can any image that you have as a file. Did I show you how to do that? You can drag it onto the.
A little bit, like you showed with that cow thing.
Yeah, we'll get to that. So basically, any file or character or any kind of image, you can click and drag onto, right onto the command line. Where is it? Oh, this is different.
Oh, so there's symbols.
Okay, yeah. So this is different. So here, what I'm doing is, there's a table of symbols, and any symbol that you can create with your keyboard with a keystroke, you can do it this way. And so I'm saying if b is greater than 1, which that was my slider to choose to turn on or off different elements. So I'm calling out the symbol, and then this will be the size of the symbol. And I'm placing the symbol at this point. All right, so which one is this? This is this one. So I'm at negative, I'm not sure what A is. A was just some parameter that I was changing to get it in the right spot. And then the height of it is basically the height of the function, and it was kind of a little offset, so I moved it down a little bit so the actual tip of the arrow was in the right place. Okay? So then as n changes, that's going to move up and down according to the value of the function.
Is that symbol already loaded into graphing?
Yeah, if you go to, where's the special characters in the edit menu? And actually you can use this in other programs. You can pull this window up and it will drop these symbols like into Microsoft Word or Excel or any other program, not just Graphing Calculator. So there's, if you look over here, I'm not sure why this is all skinny here. I don't know how to. Oh, there we go. Okay, so there's all kinds of arrows you can choose from. Parentheses, it's just the punctuation. What's really helpful is the Greek letters. Okay, and then different styles of those, math symbols, etc. So that's in, did I say edit? Edit, special characters. And that pops out. And then if I shut down Graphing Calculator, this will stay up. And like I said, you can pop those into Microsoft Word or any other thing that's taking characters. Okay. So next task then is this will be for one of the things for Monday, a generalized piecewise generator. Okay. So basically, I'm calling out breakpoints, which are x values where there's going to be a break, a change in the constant rate of change. And then here, these are the rates, the constant rates of change. So by specifying the breakpoints and specifying the rates of change, if I hit graph, it will graph the resulting graph. Right? So this one always starts at 0, 0. So the first breakpoint is the end of the first interval. Second breakpoint is the end of the second interval. So you see that here we are at 4, and the rate of change in that first interval was 0.3. Rate of change, okay? So all I have to do is come up to this here, and maybe I want this breakpoint actually to be at 5.5, and the first rate of change to be negative 0.7. etc. And maybe the second breakpoint is at 10, and then 12. So now I'm changing up the whole function. And I'll graph the new one. All I got to do is change those parameters. These are just variables that I've made character strings. We know how to do that, right? All these are variables, but I've chosen a character string to represent those parameters. Okay? So you get one more command line. You get one more command line to generate this piecewise generator. Okay? The only thing you need to know is in order to get a piecewise function, so if I want to define a function, say called f, as a piecewise function, you just hit Control A. So when you hit Control A, that's going to split it up into 2 pieces. And then every time you hit Control A after that, you get one more piece. For PC, I just Control Shift A. Thank you. PC Control Shift A. So that's really the only thing new you need to know for this, along with other things we've learned. Okay. Questions on that? So, and I have there is a full sheet that gives a full detailed explanation, and I also have a video for that one. Okay. Questions? Okay. So here's something else I've used. Who's that? You know who that is? Usain Bolt. Like a lightning bolt, right? So I recreated his race. His world record race that he ran 9.58 seconds. So let me make this a little bit. What am I looking for here? Document settings. Okay, so they had a graph that had points of his distance and time throughout the race. So I took those points and threw them to a spreadsheet, and I did a regression on those points to get a function for his distance traveled at every time between 0 and 0.58. Okay, so he basically, now I'm graphing his distance as a function of n, right? His distance from the start line and his time. So I'm trying to make time as close to actual seconds as I can as it goes. Okay, and so at 9.58, he crosses the finish line. Boom. And then he's just the athlete that he is, so he can do it over and over and over again. Okay? So, right, so 100 meter dash, the time 9.58 seconds. Okay, so ready? Here we go. Uh-oh. It's Emma. I want you to watch this. There's a point. So I want you to... Too bad that's not... The screen isn't very clear. So I want you to talk about what might I be showing with this animation? What might I be showing, or what idea am I getting at with this animation? So talk amongst yourselves.
Oh, okay.
This is his real race, right? I put a quintic to make his reproduce his real race.
Oh, okay.
Endless represents the easy could have gone the entire race to still finish the same.
Oh, to me it looked like she
Oh,
would
that's much better back there. Look at that. That version's much
Oh,
better.
okay. In the beginning it looked like she would be faster.
Yeah, she starts out going faster when she catches up. She goes the same speed.
Yeah,
She accelerates. She's going constant.
Oh, like it doesn't look constant visually when you compare it.
But for the perspective, you know, she's like,
Yeah, to me it looked like she sped up. It was wrong.
That's what I didn't do. I could
Okay, ideas. What do we think? So what am I showing by this? Oh, look like you're in the edge.
I was going to say it's a constant speed throughout from 0 to 9.58 seconds. That's what the baby's running.
The baby's running at constant speed.
It's a constant speed, yeah.
The baby's running at constant speed. Okay, what constant speed? So like, just any constant speed, or what?
No, it's a bit.
So it's the constant speed is 100 meters per 9.58 seconds. Okay, sure.
It's the average. It's Usain Bolt's average speed throughout the race.
It's Usain Bolt's average speed throughout the race. Victoria likes that. Steven likes that. Okay, so if we were talking about the idea of average speed, what would this be showing? That average speed as an idea. What is average speed, Raymond?
If they both people both travel the same time, the same distance at the same time.
Same distance at the same time. Okay. So who's representing who's representing the average speed of who? Raymond.
By the look of your projector, I'm thinking your baby is traveling at a constant speed.
Okay. So conclusion, the baby's traveling at constant speed.
So
Yeah, Jessica.
Does it mean Emma?
Emma, yeah.
Emma is representing the constant speed of Usain. Is that what you mean?
Okay, so Emma's representing the constant speed of Usain. Is Usain running at a constant speed?
No, but the average speed of Usain.
Average speed.
Yeah.
Because average speed is, what about same time, same distance? Yeah. Right, so it's the constant speed to run the same distance in the same time. Okay, and so that's what that animation shows. Okay, so here's a graph of distance versus time of Usain's race. All right, so you just got to imagine that 100 can't quite show it all. To zoom, if I zoom out, it's kind of small. But anyway, so there is, oh, you can't see that at all. Oh, wait a sec, I'm gonna have to. Okay. Just like a echo on it or something. Okay, so this is that same function. And so you told me, so what would if we graphed his average speed, what would it look like? Let's see, Kathy. So now we're going to graph, so this is his true speed profile, distance versus time profile. I want to graph his average speed. What will, for the whole race, what will that look like? Okay. Okay, so that would be the constant speed. And if I wanted to graph that, then what would the result be if I graph that? Well, how would, okay, from where to where? Okay, so in this, let's see, what's my end? 0. Kyle, did you want to add something to that?
Oh no, I was going to say if you have 2 points, 0, 0, and then at 9.58 to 100.
Right, and then okay, so that's 9.6. That's pretty good. Okay, so would the red then be the representing the average speed? Represents the average speed. So this is an average rate animator. You can pick whatever h you want, and then n is the starting value of your x coordinate. All right. So notice I can change h to be any change that I want, and then I can n will be the starting value for the average rate. Okay, and then you can just come up here and put any function you want in. So we can just do cosine x. Yeah, we're gonna need to redo the graph here. So there's a nice, if you've zoomed a lot, there's a reset graph function. So if I want to make h say a little bit smaller, say I want to make h 1.5, 1.25, that's great. And then if I change n, it gives me the average rate a little segment representing the average rate, starting at n, and over an interval of h up here. Okay, so this one, to make that, so to do this, we want to do this one in two different ways. Okay, we want to do it parametrically and also non-parametrically. So can you generate this parametrically and non-parametrically?
So we can use commas to limit x.
In the non-parametric version.
Yeah.
Sure. That's right. You'll have to, right? If you're not using parametric, then you'll have to limit x with commas. Okay. So all you have to do for this one is just change the function, and then you can change the width of your interval with h and the starting point of your interval with n. Okay. So that's the average rate animator. So we've got, what do we got? We got the reading and last, this is the last one for Wednesday. Critical précis and your reading, or did I call it critical précis, did I say?
Yeah.
And then there were some discussion questions as well. Okay, so that's for Wednesday, along with the box, the flat version, top view of the box animation of cutting the squares out. And then for Monday, you'll have the Piecewise Generator and the average rate animator. Okay, so in doing these, in every project that you do, I always try to give you the building blocks beforehand. So don't come at it like everything's new, right? So I'm trying to set you up for what you'll need to do these things. Like we talked about that one technique of a times 1 minus t plus b times t, right? And then what happened right after that? We had all these examples that utilize that, and that's something that will come up all semester. That particular example. Okay, so look for ways to use everything that we're talking about in class and building these little animations. The next one we build is going to be a more major one, okay? And that's the, well, I'll show it to you on Wednesday. So on Wednesday, I'll show you the next, which is kind of the first kind of serious animation. So I'll give you the demo, and then you'll have a week or maybe a little more to come up with that one. And that's, so I'm trying to give you all the pieces of that big one in little chunks here, and then you put it all together, okay? Questions on anything? So if you want to stick around, I can field questions. Many of you look tired, so if you want, and I've taken some extra time from you in previous days, so if you want to skedaddle, you can do that as well.
So what did H, I'm trying to figure out, like, is it the H that changes the position of the line, or is it the N? Because you have H as 2.2 and N as 2.2.
Oh, right. Coincidentally. It's just the normal meaning of H.
So H is where it changes. Okay, so it'll be N plus H. N.
Huh. That's pretty cool.
I know it is.
About note taking.
Oh, right. So have you met Janae?
Yeah.
So yeah, so she's the one you're notating for. Yeah, so once you guys get set up, then I don't have anything to do with it anymore.
Yeah, we're all set.
Oh, you guys are set up?
Yeah.
That's it. Oh, I've got a video of my baby if you want to watch my baby.
Yes.
Okay, do you have a quick question?
Oh no, it's not quick. At least I don't think it is.
Okay, so
I know you guys have been requesting that.